The fourth problem in the optimization packet takes a look at another box problem, but this box is a little different than our previous boxes. So we're given a box that has an open top. So that's a key piece of information to keep in mind, because the first time I went through and did this problem, I didn't focus on that and therefore had the wrong answers because my surface area formula was wrong. Now we're given a set volume this time. So unlike the previous box problem where we were given a fixed surface area, in a way, and asked to sort of maximize the volume, this time we're given a fixed volume and we want to find the dimensions of the box so that surface area will be minimized. All right, so if we have a box, and I'm just going to draw myself a pretty little box, and we're told that this box contains a square base. So if it's a square base, then we're going to imagine that's x by x. And then the box has a height of h, because I just picked that variable. And so the volume of this box would be x squared, because x times h. And we know that that volume equals 3,200 cubic meters. And if I were to wager, I'm going to probably want to get rid of that h value, since I like to deal in x's. So I'm going to divide by x squared and find h, just to sort of preface my work in advance. All right, so I've dealt with my constraint. Now I'm looking at surface area. So surface area of a rectangular prism, we have an open top, so this area right here does not exist. But I do have a base with the same dimensions, that would be x squared. And then I have a side over here that I've outlined in green, and that would be x times h. And that would also be over here on this side of my box. So I have two x times h's. And if I go here in the front of my box and in the back of my box, would be another x by h and an x by h. So I have another 2 times x plus times h sides. And I could simplify this a little. So I have x squared plus 4xh. And I don't want my h. I want to write this as a function of x. And so x squared plus, and I'm going to plug in my 3,200 over x squared and do a little bit of simplifying so that it's in a form that I want to take a derivative of. So here I get x squared plus 12,800 x to the negative 1. And I am now in a place where I can take a derivative using power rule and look for those critical values. So the derivative of x squared would be 2x plus negative 12,800 x to the negative 2. And I want to know when this equals 0, because that's where my critical values are. And this equation by now should be somewhat comfortable with. I'm going to add that fraction over to the left side. So I get 12,800 over x squared equals 2x. I'm going to multiply by x squared and divide by 2. So I would actually get 6,400 equals x cubed. And I would need to take the cubed root to undo that. And the cubed root of 6,400 is not an even number. It's about 18.566. And so that would be my only critical value for x. And if I go through and I do my first derivative test and I test s prime at that particular critical value, if I plug in a number like 1, 2 minus 12,000 is clearly going to come out negative. But if I were to plug in something like 100, 200, minus, and then 100 squared would be like 1,000. So that comes out, around 12. That's going to be positive. And so my function is my derivative is going from negative to positive. So my function's going from decreasing to increasing, so I have a minimum. Yes. Okay, what is the question asking us? We always go back and double check. So we want to state the dimensions of the box with a minimum surface area and the minimum surface area. Okay, so I need a box with a base of 18.566 meters by 18.566 meters and a height of, and whatever I'd get from doing 3,200 over that value squared meters, and I just don't feel like reaching for my calculator right now, would get the minimum surface area of 1,034.129 square centimeters while keeping the volume at 3,200 cubic meters. My sentence, my derivative tests, my derivative, finding my critical values, and we have solved another box problem.